Okay. So we're delighted to have Alberto Nicolis from Columbia University come tell us about a generalized Archimedean principle and the mass of sound. So Alberto got his PhD from Scuola Normale Superiore in Pisa, and then he was a postdoc at Instituto de Extraterra de Materia in Madrid, and afterwards a postdoc at Harvard. And finally, he joined the faculty of Columbia in 2007, and soon after was awarded a DOE Early Career Award. So he's an expert in gravitational physics and cosmology, but now works primarily on quantum field theories and their application to all sorts of different systems like fluids, superfluids, and so forth. So
thank you very much. It's a pleasure to be here as usual. So I want to tell you about Archimedes' principle. So it's not really cutting edge research, of course, it's more than 2,000 years old, but I want to tell you about, I want to think about it from a modern viewpoint, and I want to try and generalize it. And as a byproduct of this generalization, I will present a general formula for the mass carried by a sound wave. And I mean this in a very physical sense, literally as a displacement of mass traveling through the sound wave. So what is the general question that I want to address, and what does it have to do with the Archimedes principle? Sorry, I don't know what's going on with this. It's not working. Okay, thank you. So, what is the general question? So, the general question is one of the possible questions we might ask is: do sound waves float or sink? So, if I have a sound wave in a fluid in the presence of gravity, you know that for a normal object, I have a way to understand what are the forces acting on the object and what the resulting force is going to be, and whether that force is going to be upwards or downwards. The object is going to sink or float. And why don't we ask the same question for sound wave? Can we ask the same question for sound wave? Does it make sense to ask the same question for sound wave? So you know that for Archimedes' principle, you need usually to understand what the gravitational force acting on an object is, and what is the buoyancy force acting on that object. And then the vector sum of the two will determine whether the object will float or sink. And so if I have a wave packet or a sound wave, again, does it make sense to ask what are these two contributions to force, or even does it make sense to talk about forces acting on the sound wave? Clearly, the end point of this computation or answering this question will be to compute the trajectory of the sound wave in the presence of, in the fluid, in the presence of a gravitational field. So how do we do that? How can we approach that question? So let's go back 2,000 years, more than 2,000 years, and let's think about Archimedes' principle, okay? And so suppose I have a solid object immersed in water, let's say a potato, whatever shape, doesn't matter. And you know what matters for Archimedes' principle is the mass of the object and the volume. We call it the volume displaced. So how much fluid does it displace? And I'm sorry if this is pedantic, but I'm going through this for a reason. It's because we want to generalize, or we want to isolate the crucial feature of this phenomenon, okay, the buoyancy phenomenon. So there is a gravitational field. So clearly there's going to be a gravitational force acting on the object, and there's going to be pressure forces. And the gravitational force, it's simple to compute. As usual, it's the mass times the gravitational acceleration, and it's going down. And the buoyancy force, even though formally it looks very complicated because you're supposed to integrate the pressure forces over the whole surface, and the pressure depends on that. In practice, you know that it sums up to being the density of the fluid that you displace, the volume of the fluid that you displace, and times again the gravitational acceleration, but this time going up. And the vector sum of these two forces will give you a small remainder, small or large, depending on the densities, of course. And if the remainder is down, you go down. If the remainder is up, you go up. Okay. So now, suppose you want to, suppose you want to do the same for a more general object. This more general object could be, like I was saying, a wave packet of some sort of wave that lives in the fluid, for example, a sound wave. But it could even be, for example, a quantum particle. How do I determine buoyancy for an electron immersed in a fluid? It's not obvious. Okay, for instance, in particular,
Has it been motivated by something real, or you just fool around?
I just fool around.
Okay,
Okay.
I just wanted to know. Okay.
Well, I fool around with the real systems,
Yeah, that's
as opposed to fooling around with the imaginary system, which is usually what I do. So. Okay, so yeah, I want to understand buoyancy phenomena for more general objects.
okay.
Okay, makes sense. Okay, so for example, a quantum particle, let's say an electron immersed in a fluid, let's say in liquid helium, in a superfluid even. So we know the electron is described by a wave function. So maybe for the electron, we know what the mass is. For sure, we know what the mass of an electron is, and so the gravitational force part of the Archimedes principle, this we know. But what is the volume displaced by a wave function? Or for a sound wave, for a wave packet, what is the volume displaced by a wave packet, and what is the mass associated with the wave packet?
Can I ask you about the subatomic particle, which is, for me, a fluid is something that's comprised of atoms, at least,
Yes,
right?
yes.
So I don't know what it makes sense to talk about the buoyant force on an electron in a fluid, right?
That's a good point, but suppose I give you an electron in a zero temperature superfluid, in which the particle nature of the superfluid is almost not there, meaning the superfluid is described by a completely delocalized wave function itself, and so in a sense it makes sense to describe it as some sort of medium.
Sure, but
It's
then
a good point.
But
Yeah.
then I don't know that I could go back and use that F equals rho V times G, because that came from pressure and all sorts of
Exactly.
things.
So I'm saying that all these are. My point will be that this is ill-defined and luckily unnecessary. Okay. But yeah, it's an excellent point. So if you want, the scale of your quantum particle is smaller than the, I don't know, the interatomic separation, then we have to be more careful. You're right. Yeah. So let's that's an excellent point. So let's think about classical waves. Okay, long wavelength, longer wavelengths longer than the interatomic separation, but still fairly localized, so I can think of them as an object propagating. Let's say some sort of geometric optics, geometric acoustics. Okay, so so for waves or for particles, this is not, these two quantities are not particularly well defined. And so I want to show you an example of a normal object for which these two quantities are well defined, but in fact are kind of ambiguous because they depend on how you look at the object. Okay, and the object is the humble sponge. Okay, so let's take a kitchen sponge, like some rectangular sponge, and I can look at it from two different viewpoints. There is a viewpoint in which, if I really look at it close up, I see that there is some sort of grid structure. I'm simplifying, of course, but there is a lot of cavities in a dry sponge. And when I think about the sponge, before I immerse it in water, when I think about the sponge, when it's dry, the mass is pretty small. The mass of a dry sponge is pretty small. And the volume that the sponge, the solid material of the sponge will displace when I put it in water is going to be pretty small because the sponge is mostly cavities. Okay, and so when I think about the sponge in water now, I throw the sponge in the sink, it's in water, and I think about the two contributions to Archimedes' principle. The gravitational force is pretty small because the mass is so small, but the volume displaced is almost pretty small. The net result will be a small sinking force for the sponge. But there's an equivalent but completely different viewpoint, some more macroscopic viewpoint. Suppose you don't have the resolution to see that the sponge has many cavities, okay, and you only know the sponge in water. This is really very relevant for us because, for instance, sound waves only exist in the medium, so I cannot think of the dry version of a sound wave. A sound wave without the medium does not exist. So let's think about the sponge in water directly. Well, there is a more macroscopic description in which I have a heavy sponge that has soaked up a lot of water, and there's a lot of mass there. And correspondingly, the volume that heavy sponge displaces is the whole slab, it's the whole rectangular volume occupied by the sponge. So now the two contributions to the Archimedes principle are big, but their remainder, their vector sum is the same as before. These are two equivalent viewpoints that lead the same result, but they are very different. In particular, they split up. The only observable that you have in water, which is the net force that a scale will detect in water, they split up these observable into two contributions that are not observable in water. So, I mean, those of you who are familiar with quantum field theory, in particular physics, let's say, will notice that this is some sort of analog renormalization in the sense that there is one observable physical quantity that I can measure, and this should be well defined. And the way I compute it might involve quantities that are not completely well defined, that are not observable directly. And they are ambiguous in the sense that depending on how I look at the system, in particular the scale at which I look at the system, yes, here I'm looking at the system microscopically, here I'm looking at the system at a different scale. Depending on the scale at which I look at the system, these unobservable intermediate contributions that I have to compute are different, but the net result, the physical observable quantity, is the same in both cases. This is to say that maybe when we now want to generalize the Archimedean principle to more general objects, it doesn't make much sense to focus on these two contributions. Maybe we can get away by computing directly the physical observable, which in the case of a wave would be, let's say, the trajectory of the wave. Is this clear? The sponge example. Okay, so yeah, this is what I just said, that the only observable is really the net force. The only observable in water is the net force. You cannot observe, you cannot measure the two contributions separately. And then maybe this is good for us because it's not obvious what those two contributions are for the more general object.
On the example of the wave, one could imagine that the shape of the wave function itself will be distorted too. If you initiated a wave, that as it propagates,
Yes.
it won't just go up or down as you're imagining, but it will actually get distorted. And somehow I don't see how you even define the wave. Your sponge example was nice because we could still imagine
Yes.
adjusting.
But let's see. So when we think about wave propagation in media, like electromagnetic waves, no? So in the geometric optics limit for a wave packet, you could say exactly the same words, but at the level of checking what the trajectory is, it doesn't matter how the wave packet is.
But I'm realizing there's even how to define an analog of the center of mass to talk about the trajectory. It's not so obvious to me how you would even define that.
Yes.
It's true in the geometric optics limit.
Yes. But this is true for any wave packet. For instance, even when we talk about an electron in quantum mechanics, there is a sense in which, yeah, if we
Well,
want
if you
to
know the whole wave function, then that's what you know.
correct, but on the
And
other
you're
end,
not talking, somehow you're abstracting it from needing to know the whole wave function. You're talking like there's a single property, sort of a center of mass.
yes,
And I'm
exactly.
failing to
So
see
in the logic of effective theories, in particular, this will be an effective point particle theory. When I look at the system at this wave packet from far away and it's localized, in the same sense as when I say, there is a photon coming from there to there and it's fairly localized, I don't need to know much about the structure, the internal structure of this wave packet. Only some integrated quantities will be important, the energy, the momentum. Do you agree that
Right,
for
you're talking
photons-
more like position, but I agree with you about energy and stuff. Yeah, okay, I'll let you go ahead.
Yeah, no, I see what you mean, but when we talk about a photon going, so when I turn off the light, okay, the last photon emitted is the couch at a certain time, and that's it. So it's a fairly localized particle, right? It's not that I have to work in a eigenstate of energy.
Okay, so you're
momentum
in the,
completely localized.
I'm happy, you just want to treat it as like, you're considering systems that are very well localized. Just talking about.
In the sense, in the usual sense of, yeah, following the trajectory of a wave in the geometric optics or geometric
I
acoustics.
can ask at the end.
Yes. Okay, so now the question is there a way to compute directly the effect of buoyancy or the effect of gravity or the combined effect of these two things on an excitation in a fluid without knowing much about, as we were saying, the internal structure of this excitation? And the logic is that of effective point particle theories, which is some sort of dynamical, systematic generalization of the multiple expansion. So for instance, in electrostatics, we are used to the idea that if I have a fairly localized source of charges, and I look at it from large distances so that it looks very small, okay, in first approximation, I can replace it with a monopole, which is the total charge of the system. Then the next correction will be a dipole moment, it will give me a field that decays faster, 1 over r, the quadrupole, and so on. Okay, and so the same is true for a dynamical situation in which I have some sort of localized objects that move through space, and I want to describe the motion and the dynamics of this object, the way it interacts with the external fields of this object, in the limit in which this object is small compared to any other scale, for instance, the scale of other perturbations in the system. Okay, and I want to do it with the Lagrangian or Hamiltonian rather than the equations of motion, because that's more powerful. If I am given the action of the Hamiltonian of the system, not only I can derive the equations of motion, but I can also derive conservation laws, because Noether theorem requires a Lagrangian or Hamiltonian formalism to relate symmetries to conservation laws. And I can couple whatever system I'm given the Lagrangian of to other systems systematically, for instance, external electromagnetic fields or external gravitational fields. Whereas if I'm only given the equations of motion, there is no systematic way of coupling different equations of motion. Sorry, equations of motion for different systems in a consistent way. And finally, quantum mechanics, or in general quantum theory, we can only do with Hamiltonians or Lagrangians. We cannot do directly with equations of motion. There's no sense in which we can quantize Newton's equations. Okay, we need a Hamiltonian. So I want to write down an effective Lagrangian or Hamiltonian for a generic object living in a fluid
Without dissipation.
Without dissipation. So dissipation in hydrodynamics is a high-speed, short-distance phenomenon, in the sense that viscosity and the heat conduction, let's say, appears as a higher derivative correction compared to perfect fluid hydrodynamics. So let's say that in first approximation. Yes, then for instance, for a sound wave has a dispersion relation CSK plus something proportional to K square. So at long enough wavelengths, the effects of viscosity, which is that K square, goes to 0. Compared to the, if you want, the quality factor becomes better and better at low frequencies.
Which is the opposite limit of localization.
Yes, of course. I mean, good. So there is a microscopic, let's say you take a weakly coupled glass, let's say air, okay? There is a microscopic scale, which is the mean-free path. Hydrodynamics applies only at distances longer than the mean-free path. And that's the limit in which you can talk about sound waves and small viscosity if you want. And so you want a wave packet that is a long-lived sound wave. For instance, the sound waves that we are exchanging are in that limit, right? They are long-lived, so they can get from me to you. But on the other hand, I mean, when I say a letter, it lasts less than a second, so it's a fairly localized wave packet compared to perhaps other perturbations. So it's an in-between limit. But that's always the case. Now, when we talk about wave packets in any medium, it's always this mixed limit of long wavelength compared to the mean-free path, short wavelengths compared to other scales. Okay, so I want to write a general effective Lagrangian for an object, whatever object means living in a fluid, and there's going to be some universal features and there's going to be some model-dependent features. What do I mean? There's going to be some features of this Lagrangian that just follow from the symmetries, and as we will see, Galilean boosts are also important. Of course, in a fluid, the Galilean boosts are broken, but they are broken by the fluid. And so, for example, the velocity with respect to the fluid is invariant under overall Galilean boosts, but the velocity without taking into account the relative velocity of the fluid, this is not invariant. And so there's going to be some universal features of this Lagrangian that are following from the symmetries, and there's going to be some model-dependent features which depend on the object that you're talking about that are model-dependent. So different objects will have different parameters, if you want, in this Lagrangian. But the symmetries of that Lagrangian should be the same for all objects. And I want to start without gravity. So let's forget for a second about Archimedes principle, because as we will see, gravity is an add-on that is very actually easy to implement, thanks to the magical properties of hydrostatics that I will tell you.
Are you just going to go to an accelerating
Am I? No.
to get gravity and you just go to an accelerating? Right?
No, I don't know if it's related, but in hydrostatics, the magic will be this. In hydrostatics, the local pressure is algebraically related to the local value of the Newtonian potential. Hydrostatic equilibrium, I mean, we're used to it, so we don't think about it, but at the level of differential equations is a very special property that only fluids have, that the local value of the gravitational potential completely determines the local pressure, instead of there being some sort of Green's function. But we will see in a second. Okay. I don't know if this is can be phrased as going to be accelerated frame. I don't think so, but yeah, okay. So here's the claim. The claim is this, that the Lagrangian for a point particle of position x of t, and again, there is some ambiguity, Glenn, is in how to define what we mean by the center of this wave packet, but when the wave packet is small, we don't care much. In the same sense, there are ambiguities in defining the center of a multipolar charge distribution. We know that the monopole is completely independent, the dipole and the other multiples change a little bit if you move the center around, but again, everything is systematic regardless of the origin that you choose, as long as you don't choose the origin here, as long as you choose it in the right neighborhood, let's say. Okay, so here's the claim for a point particle of position x and velocity x dot. The Lagrangian, based on symmetries, the Lagrangian for this particle living in a fluid should be a generic function of x dot minus the fluid velocity field. So this is the relative velocity, and with coefficients that depend on x, on the position of the particle, only through observable quantities of the fluid. For example, the density of the fluid. So if the fluid is completely homogeneous, of course, it doesn't matter where I put my particle. So the Lagrangian will not depend on the position of my particle. If the density or other properties of the fluid, I'm assuming barotropic equation of states, so the only independent scalar quantity is the density, or the number density or the pressure, one of them. So if the density depends on position, the properties of the coefficients of my Lagrangian function will depend on position through the value of the density.
So are we assuming that the wave doesn't change the density of the fluid?
So this is in some sort of probe limit in which the wave is just propagating through the fluid.
Right, but like a sound wave changes the density.
Correct. So it can be, we'll talk about that, but somehow everything will be same consistent in perturbation theory, order by order, you can take that into account.
Okay.
In the sense, in the following sense. So if so this is in addition to the Lagrangian of the system. So I'm not writing the Lagrangian for the fluid here, but there is this localized on the trajectory, plus the Lagrangian for the fluid. This, the presence of the particle itself, because of this coupling to the density, sources the density of the fluid, and so perturbs the density of the fluid. So it will be in perturbation theory, you can compute all these effects. Okay.
And by density there, do you literally mean the fluid density, or do you mean all of the intrinsic properties of the fluid at the point?
So I'm assuming that
Like
for
chemical chemistry, for instance.
exactly. So I'm assuming a barotropic equation of state. So there's only
There
one
is no
independent thermodynamic for simplicity.
Right.
Okay. For simplicity. Okay. So now, related to this, now, so when the density now is a field by itself, so it can depend on x and t, and the velocity of the fluid, the local velocity of the fluid depends on x and t. This encodes all possible interactions of this perturbation with the surrounding fluid. So if I have a very long wavelength, let's say, perturbation, let's say a very long sound wave through which my object, which could be a much shorter sound wave, is propagating, I can use this Lagrangian to compute in perturbation theory, or beyond the perturbation theory if I want, the trajectory of this object, how this object sources these perturbations, how this object scatters these perturbations, and so on. Okay? This is a Lagrangian that is valid for fluid perturbations of much longer wavelengths compared to the object itself. Of course, if there is no separation of scales, it's impossible to treat the object as a small point particle plus multipolar corrections. Okay, so this is the claim. So if you investigate the symmetries of the system, you discover that in the non-relativistic limit, this is the most general Lagrangian you get. There's also a relativistic generalization if one is interested in relativistic fluids, but I'm doing the non-relativistic case for simplicity. So now let's revisit Archimedes' principle 2000 years later in this language. Okay, let's see how magically it arises. Of course, this will be like a very contrived way to derive Archimedes' principle, but at least since it's based on the Lagrangian, I know how to generalize it without ever invoking forces acting on my objects. So suppose I give you an ordinary object in a fluid. Now, what do I mean by ordinary? I mean, from the viewpoint of Lagrangians, I mean something that has a Lagrangian of an ordinary object. What is the Lagrangian of an ordinary object? So let's for a second forget about these two terms. In empty space, the Lagrangian of a free object, first approximation, if I forget, for instance, rotational degrees of freedom, which are some sort of higher order things in this point particle limit. So in the point particle limit, the Lagrangian of an object is just the kinetic energy. When I immerse the object in a fluid, at least at slow speeds compared to the speed of sound in the fluid, you can convince yourself that there are two effects. One is this, that when you are immersed in a fluid, your mass, your total mass, gets renormalized. So why is it difficult, for instance? So suppose you are in a swimming pool, okay, that is up to here, the water, and you're trying to walk. And it's very difficult. Why is it difficult? Well, the first guess is that there's viscosity. But viscosity is negligible at low speeds. So and at large distances, so you're very big compared to the microscopic scales of water, and you're moving at low speeds, so viscosity is completely negligible. It's very hard to walk in water because of your boundary conditions, you are carrying, sorry. you're carrying with you a lot of fluid. You're carrying with you something of order of your volume times the density of water. So essentially, you're carrying twice your mass when you try to walk through water.
But
And
so once you reach the terminal velocity, you should apply no effort and you will walk through water as if through air.
Is this a quote or is this?
This is a conclusion from what you said, which is obviously wrong, right? Because this additional mass will make it harder to accelerate. But once you go with a constant velocity, there should be no problem moving through water, and detained so. The reason why it is difficult to walk through water is, of course, turbulent resistance,
There is that, but
not the additional mass.
no, but when you walk very slowly and you start, like if I start from zero, there is no turbulence. Now I move. Are you saying I immediately create a lot of turbulence?
What you have described the fact that you become a little bit heavier, but the resistance force is a thing which is totally independent of the additional mass. Anyway, we can talk afterwards. That's okay.
No, but I'm not talking about some. So in this limit, in which if you want, eventually I'm going to do hydrostatics. Okay, I'm going to do an object at rest. So
I'm just saying mv squared does not explain why it is hard to walk through water. It is explained by turbulent resistance.
I am not sure.
Because this
Okay,
would
we
only
can
be,
talk
this would
after.
only appear if you were changing, this would only affect your dynamics.
Of
When you're
course.
changing your velocity.
But anyway,
It doesn't
there-
affect the dynamics. that
There was a
comes to
period in
the
my life when I was very into pendulums. And so one of the corrections to the pendulum is an additional mass term from dragging the air along with you. It acts like a mass. And then when you get to the end, the air you drag along with you pushes you forward a little bit. So there is this term. It's just not as
It only
big when you're
happens
walking
when
on the
you're-
pool as
it only
it
affects
is
By the way,
changing
so
your
this is
velocity.
not the okay. This is Landau and Lifshitz. I don't know if this can. I certainly did not come up with this. Okay, so then what you're saying is certainly an effect, but the fact that your mass gets renormalized of order one, that is a non-effect.
I'm only arguing with your logic that this is what makes it hard to walk through water. What
This-
makes it hard to walk through water is simple resistance.
Okay, so maybe there are these two
Okay,
effects.
yeah.
Okay. Anyway, okay. Let's not talk about walking through water. Do you agree that there is a term like this?
Yes.
Okay, great. Okay. And then there is a term like this. So where is this coming from? Well, it comes from the fact that if you want to, so the energy, if you want, of an object in water depends on the local pressure, in the sense that if I change the position of the object, for example, in places of different pressures, its energy will change according to this term. In particular, if I take an object from outside the fluid and I immerse it into the fluid, this is the work done against pressure forces. Do you agree with this?
I'm just a listener.
Okay, so now remember, so this, by the way, this is not of the format I advertised earlier. So earlier I advertised this form, just a function of the relative velocity and the local density. This is not of that form, and it's because the free Lagrangian of an object in empty space is invariant under Galilean transformations only up to total derivatives, in the sense that if I boost my x in some direction, so x dot gets an extra v. Okay, so this Lagrangian changes by m v x dot, which is a total derivative, but it's not strictly invariant. However, you can convince yourself that you can manipulate a little bit this Lagrangian and use the Euler equation in the form of Bernoulli, and rewrite it exactly in the advertised form up to total time derivatives, which do not contribute to the equation solution. So now there is a mass plus the correction to the mass, so there is normalized mass, multiplying the relative velocity square. There is the work done against pressure forces, And then there is this new term that came from these here manipulating things and rewriting in terms of this invariant Galilean invariant velocity times this function of rho. What is this function of rho? It's a particular integral. It's the integral of 1 over rho in dp. Simply because in the Euler equation there is gradient of p over rho. So when you integrate that, you get this function. It doesn't matter much to compute this function, okay? As we will see, it's directly related to the Newtonian potential in the presence of time. But so, just to say that there is a way to write the Lagrangian of an ordinary object in a fluid precisely in the form that I advertised before: relative velocity square and a function of the density.
This app is allowed to depend on spatial derivatives of rho and u.
Special, yeah, that would be at higher orders in this expansion. So remember, we are doing an expansion in which rho and u vary over scales that are much longer than the size of your object. So those would be like multiple couplings, like dipole, quadrupole, etc. So this is the analog of the monopole. Okay. Okay. So now how do we introduce gravity? Well, it's very easy because of that magic that I was alluding to before. So you have a gravitational acceleration that is minus the gradient of the Newtonian potential. And in hydrostatics, so for a fluid at rest, the pressure should adjust locally in order to obey this equation. But remember what we said before, that W function that I just introduced was exactly the integral of 1 over rho in dp. So the gradient of W is directly related to the gradient of rho, to the gradient of phi, sorry. And the pressure is directly related, the gradient of the pressure is related to the gradient of phi also, but the pressure is a function of density, and so it means that both P and W are related algebraically.
What W was?
So W is simply a new thermodynamic quantity that I'm defining, is the integral of 1 over rho in dp. If you know how the pressure depends on rho, take any arbitrary reference pressure to start from. So a reference density, so let's say W of rho is arbitrary reference density up to rho dp of rho prime over rho prime.
It's called enthalpy.
No, is it?
Yeah.
dp over rho. Yes. Is the enthalpy. W usually. I chose W, but not because I thought it was not the enthalpy. Because it's exactly the enthalpy.
It depends, of course, at what constant you do the int.
No, but wait, but the enthalpy should have the same units as P, no? But this is dimensionless, or this is there's units of in normativistic limit is a different unit. So maybe it's the enthalpy per unit mass or something like that.
It's if you do it at constant entropy, then it's called enthalpy. Yes, but whatever, it doesn't matter. Who cares? What is it called?
Well, you brought it up.
Didn't you say? Didn't you say, Robin, it's enthalpy? Did I remember correctly?
Okay. Anyway, so let's say it's the enthalpy, or it's a thermodynamic quantity. It's completely determined locally by density. On the other hand, the hydrostatic equilibrium forces both the pressure and this enthalpy, and therefore rho, to be completely determined by the local value of phi. Okay, but algebraically, because well, this is clear for W, no? So the gradient up to a constant, an arbitrary constant, if the gradient of W is the same as the gradient of phi, it means that W is phi locally up to a arbitrary constant. And so that's it, because now, what is the net gravitational force? At this point, you see, I don't need to talk about the individual contributions to the forces. I have a Lagrangian, and I derive the Lagrangian with respect to x, and I know that in the Euler-Lagrange equation, okay, I have dVt related to Lagrangian with respect to x dot. This is precisely by definition of the momentum of my particle, that equals dl over dx. So my equation is ddt of p equals dl over dx, and this is the derivative of the time derivative of momentum is what I usually call the force in a mechanical system. Okay, I don't need to have to solve this equation and find the trajectories. I don't need to have the force interpretation, but that's what I usually call the force, at least for a mechanical system. Okay, so I can just compute the derivative, and the Lagrangian now depends on x. Remember, only through the fields, the rho and u field. So I'm looking at the fluid at equilibrium, static equilibrium. So u is 0. Rho depends on x. How does it depend on x? Well, because phi depends on x vertically, and everything else depends on x only through phi. So all derivatives with respect to x go through phi, and this g is the gradient of phi. And if you take the Lagrange I gave you before, you get gm minus rho v, which is exactly the gravitational force minus the buoyancy force. So this is how we recover Archimedes' principle from this point particle Lagrangian in a fluid. Okay, and remember, so far I used the symmetries to describe, to tell you that a generic Lagrangian should take this form, and then I used some sort of mechanical intuition to write down the Lagrangian for an ordinary object, or at least this is what I call an ordinary object, something with this Lagrangian. When I think about this solid moving and being immersed in a fluid, I know that these are the different contributions to the Lagrangian. So now, if I have a generalized object, if I'm able to understand what the Lagrangian should look like for this object in a fluid, I'm in business and I can compute through exactly the same logic the variation, the time derivative of the momentum of that object, simply by taking the derivative of Lagrangian with respect to x. And the derivative of Lagrangian with respect to x, as I said, only comes from the Newtonian potential. And the derivative with respect to Newtonian potential only comes from the density. So this is g, or minus g. And this is the coefficient that determines how the object responds to an external gravitational field. This is the net effect. It doesn't separate into gravitational force and buoyancy. As we saw in this example, this is the net effect. So this way you can compute the net effect of gravity on an object. Okay. So now I can apply to more general objects, in particular sound waves. It so happens that it's easier to work with the Hamiltonian rather than the Lagrangian, but the logic is pretty much the same. Okay. And so if you go through this example that I just gave you here, dp over dt is, if you know what the energy of an object is as a function of its momentum and the local density of the fluid, if you go through exactly this logic, you find that the time derivative of the momentum is, by Hamilton's equations, minus the derivative of the Hamiltonian with respect to x. The energy depends on x only through the density, and the density only depends on x because the gravitational field depends on x. If you put everything together, you find this relationship. That what you normally call the force, so the variation of the momentum with respect to time, is the gravitational acceleration times some effective, let's call it gravitational mass, because for a normal particle, this is the mass. Some effective gravitational mass, which has a very compact formula. It tells you, it says that you should compute the derivative of the energy with respect to rho at given p, and I will give you an example in a second. And then there is this E over CS square. Now compare, I mean, this is reminiscent of Einstein's E equals mc squared. Now, so this is telling you that m is E over CS squared, so at least it has the right dimensions, and it's not relativistic because this is the speed of sound, not the speed of light. And there is a coefficient in front, which is this logarithmic derivative. That's the claim. So for example, for a sound wave, I'm sorry, before I get there, so once you're given the energy as a function of P of rho, so the claim is that the effective gravitational mass, meaning the coefficient in front of the gradient of phi that determines what the trajectory of an object looks like, is this quantity. And then the equation of motion is simply this, which is an incredibly simple equation of motion. So the only thing that you need to know is how the energy depends on momentum and rho. So let me give you an example. Suppose I give you a sound wave packet. Okay. Well, what is the energy as a function of P and rho? Well, if I think about first dispersion relations and then I use some sort of quantum mechanics intuition in the sense that omega, h bar omega becomes energy and h bar k becomes P, I can guess it right away. I know that for a sound wave, or in a fluid at rest, the frequency is the speed of sound times k. And so the guess is that the energy of a sound wave of given momentum P as a function of rho also is the rho dependent sound speed times P. And as a check, if you compute the velocity of the sound wave simply by taking the derivative with respect to momentum, you immediately get CSP, which is the correct velocity of a sound wave with momentum P. It's independent of the absolute value of the momentum, so it travels at the speed of sound in the direction of the momentum.
Sorry, I don't mean to give you a hard time here, but you've said a wave packet.
Yeah.
And you've written relation that V equals omega K, which is for a plane wave, not a wave packet.
Yeah.
Right, wave packet, it would be V equals D omega.
Which is this? So d omega over d over dp is the same as d omega over dk. For a linear dispersion relation in which omega is linear in k, the group velocity and the phase velocity are exactly the same.
Yes, that's true.
In general, in this way, you always get the group velocity, which is what you're interested in, right? By taking the derivative. So if you want the first Hamilton's equation, x dot equals d over
Right.
dp is giving you the group velocity.
Right, but like water, famously, that's not true, right?
Water,
The speed of sound in water is a function of wavelength.
that's a higher derivative effect in the sense that it starts like this.
That's why I can't be an Olympic swimmer.
It starts like this, and then you have a cube.
Yes, that's the only reason why.
What?
If you're tall, because the speed of sound is faster when you're long, because long sailboats are faster.
No, those are surface waves. Those are not sound waves. Those are the
Oh, right. Sorry.
waves on the surface. Those go, yeah, good. Those go like square root of k.
But the sound waves get deflected up to the surface
Yes,
in a gradient because the gradient changes the velocity of sound with depth.
yes,
That's why sound goes floats.
yes. So as I will write in my next slide. So it's exactly this effect is exactly equivalent to that. It's exactly the same formula in different language. But my claim is that there is a sense in which this is gravity. And it's this, if I go back to the Lagrangian, so remember, in hydrostatics, rho can be expressed completely in terms of phi. Okay, the local value of rho is related to the local value of the Newton potential. So since it's an addition, this is a term in the Lagrangian of the system, of the coupled system fluid plus particle, I claim that this is also a source for gravity, meaning I claim that this mass is a very physical mass that is traveling with the wave, and in principle, so it's a small fraction of the mass of the fluid that is traveling with the wave, and its source is gravity with enough. It's a prediction. So you could in principle measure the gravitational field that is traveling with this wave. By the way, and it's in general a negative mass because for normal equations of state, the speed of sound increases with density. That's the claim.
What you would trigger, right? It's negative.
Excuse me?
It's negative.
Well, it's negative in the sense that as it travels, it leaves behind some mass, right? So it's as if it's sucking some mass. So the wave travels and it's sucking some mass in the opposite direction. And so when you measure, like that's the claim, when you measure the gravitational field of a fluid, of course, there is the bulk of the fluid which creates some gravity, but when there is a sound wave packet, there should be it's as if it's traveling under density, so there should be a dip in the gravitational potential traveling with the wave packet. Of course, the question is, can we measure it? But that's the claim. I claim that this is a very physical mass. And the claim is very physical because we checked in a number of ways. So in particular, you can take the hydrodynamics equation, so the continuity equation and the Euler equation. Forget about all these Lagranges, etc. Just take the equations of fluid dynamics and expand without gravity and expand about equilibrium. Okay, you know that at linear order there are wave solutions, and of course at linear order, if you compute the perturbation in the density and you integrate over a large enough volume that contains your wave packet, well, the perturbation in the density will integrate to zero because at linear order you have cosine or sine, whatever, and the average is zero. Okay. However, when you consider now the quadratic terms, nonlinear terms in particular in the Euler equation, but let's say quadratic terms in the Euler equation, perturbatively you can compute the quadratic corrections to this integral. Okay. And so at linear order you get zero, and at quadratic order you get something that is exactly that formula. And you see from here that this is a nonlinear effect from the viewpoint of wave mechanics, because the speed of sound, the derivative of the speed of sound with respect to the density is precisely what controls the size of the first nonlinearities in the Euler equation. If the speed of sound were constant for different densities, the equation of hydrodynamics would be linear. So it's a nonlinear effect. From the viewpoint of wave mechanics, it's a nonlinear effect. But it's a very physical mass. It's the integral of the mass density perturbation over a volume that encompasses the wave packet. That's the claim. Yeah.
So if I make a sound underwater, if I understand you correctly, you're saying this will radiate out some waves.
Yeah.
They'll accelerate upwards through this effect. But I should really interpret this as a physical underdensity. They really have negative mass with respect to the fluid at rest. On the other hand, the total mass of the fluid is not affected by making the sound.
Yeah, so it means that there's going to be some compensating flow of fluid.
Where is it?
Well, I haven't solved the equations everywhere, but is there a? My guess would be, let's say we take a finite volume, because in infinite volume, of course, the mass is infinite, so it's not obvious what it means that it's conserved, right? Let's take a finite volume. Okay, and let's say there's a speaker here. Okay, and we emit some sound wave, and so I think this is what I think, but I haven't done the computation. I think that this transfer of mass should be compensating by something happening far away. By the way, again, if you read between the lines in Landau and Lifshitz fluid mechanics, they don't find this formula, but they do find that because of how momentum conservation, because of momentum transfer, energy transfer for the surface, how they work, they claim at some point there should be an associated transfer of mass associated with the wave. But they leave it like that as a vague statement. I think this effect is there. And I agree with you that it's kind of subtle to understand how it's compensated, but I don't have a completely satisfactory answer for now. Okay. So.
Is it required that the fluid be compressible here?
Well, remember, incompressibility means infinite speed of sound. So I'm not sure exactly how to talk about sound waves at infinite speed. I mean, it's a subtle link. Incompressibility is a subtle link.
But so then, like, is it wrong to think of this as if the speed of sound changes with density and density changes with depth because of pressure, because the fluid's compressible, then I can just think of this as like refraction.
No, that's exactly
That's
what
what
you're saying.
Yeah, so is that?
And I
that's
agree
the answer?
completely. So let me get to this slide, okay?
But that's not.
Oh, okay, there we go.
Okay.
And that's certainly a big effect. Certainly.
Okay, so exactly what you guys are saying. So when in a situation in which I have a gravitational field, all these quantities depend on z, okay? And there is a very famous Snell's law that, in fact, in this language, it's obvious where it comes from. It comes from conservation of energy, because this situation only breaks spatial translations in the vertical direction. So energy is conserved and horizontal momentum is conserved. Combine these two, you get Snell's law. Okay, so refraction in the form of Snell's law is, as you guys are saying, a very well-known phenomenon, and the trajectory that you get is exactly the same as the one I get with this effect. So the two effects, from the viewpoint of the trajectory of your sound wave, are exactly the same. But I claim that there is a very physical sense in which there is a mass associated with this traveling wave, because A, I computed it also solving non-linearly the Euler equation, the quadratic order, and B, it comes from a term in the Lagrange that couples your point particle to the gravitational field, and so not only the gravitational field affects the trajectory of your point particle, but your point particle sources the gravitational field. So in a sense, yes, from the viewpoint of the trajectory, it is a refraction, but there is an extra effect. There is a I claim that there is a transfer of mass. Does that answer your question?
Sure.
Sure. You don't sound very convinced.
I'm trying to think how it's a transfer of mass. Phonons have mass. That's possible.
Yeah, that's the claim. So here's claim that sources, since it sources gravity, it should transfer mass. Here's my last slide. Here's a fun generalization. So consider rotons in liquid helium. So what are rotons? Well, this is the spectrum of elementary excitations in superfluid helium-4. So as a function of momentum, you have an energy that starts linear, and these are the phonons, and the slope here is CS, the speed of sound. And then it has some funny shape. In particular, there is a minimum at finite energy and finite momentum. And this delta in units of temperature is of order 50 Kelvin, if I remember correctly. Anyway, it's something like 10 Kelvin, so well above the transition temperature for it, a few times above the transition temperature. Anyway, so why is this minimum interesting? So suppose you look at excitations close to this minimum. So they have finite momentum, but it's a minimum of energy. Well, these are called rotons. So their velocity, and we go back now to the group velocity, is the derivative of the energy with respect to the momentum. And depending on whether you are to the right or to the left of the minimum, this derivative is either positive or negative, which means that the velocity of these particles is either aligned or anti-aligned with momentum, depending on where we are in this dispersion curve. Okay? It can also be zero. So you can have, if you are exactly at the minimum, you have finite momentum, but zero velocities. Okay, so why is it interesting? Because now suppose I redo all these analyses that I told you, but for these rotons. So I go here, I take, here's my formula, general formula for the gravitational mass of an object, the derivative of the energy with respect to the density, energy divided by c squared. I plug it in, I have the Hamiltonian for the rotons, which is, this is the Hamiltonian for the rotons, okay? Energy as a function of momentum is the Hamiltonian of the rotons, where this delta, the only dependence or rho comes from delta and from the curvature of this, how they change the rho. Anyway, so you can plug in numbers for liquid helium, and it turns out to be of order of the energy of the roton divided by c squared, and in particular positive. So a positive net mass, gravitational mass, tells you that these things should sink. However, because their velocity can be anti-aligned with momentum, the actual trajectories that they perform can be very complicated, because remember, the equation of motion was dp over dt equals gravitational mass G. So this equation tells us how momentum evolves, but the velocity is related to momentum in a funny way. In particular, if momentum evolves in a way that you go from the right to the left, you go to a turning point in which, while momentum keeps evolving, maybe down, because G pulls the momentum down, if going down, you cross this point, the velocity changes sign. So you start evolving in crazy ways. So this is the most obvious trajectory you might have, depending on where you start in this curve, where you reach a moment. But you can also have these crazy trajectories here. So these are trajectories of rotons falling in the gravitational field of Earth. Again, is this measurable? I don't know, because the scales here are very long compared to the scales in which we usually deal with liquid helium. So I don't think it's realistic. But this shows how somehow the Archimedes principle can be quite generalized suitably to generic objects, can have quite unusual implications. So I think the interesting question is this. So at least for a number of some reasons. So it's the effect that I'm telling you about here is complete, at least for ordinary sound waves, is completely equivalent to Snell's law, so to refraction, but it also has some implications in terms of displacement of mass, and in particular the fact that this is really gravitational mass. So if a chunk of the Newtonian mass of the fluid in which these excitations are moving, and its source is gravity. Of course, for sound waves in an ordinary fluid, it's very difficult to detect the perturbations in the gravitational field. But maybe when we look at geophysical situations, I don't know, seismic waves, maybe one can measure it. In particular, at some point we were talking with our LIGO colleagues to see and try to understand what happens if a seismic wave travels under LIGO. Can one measure this? Thank you very much.
Aren't the higher derivative terms important for rotons? Precisely because
derivatives in
it's a sort of a cutoff effect, right? So the momentum where this happens isn't that the momentum where the derivative expansion breaks down?
No, so the point is this. So there is because this slope, the slope that goes from the origin to here, is smaller than this slope, you can prove that if you are close enough to the minimum, these are exactly stable. So they cannot decay into photons. And so at that point, the effective theory of a single roton coupled to external fields is well defined. You have a stable particle with some parameters, these are measurable parameters, and coupled to long wavelength perturbations. This is well defined. You agree with this?
So it's the delta P that matters, you're saying, from the minimum.
Yeah. You don't want to go too far. Yeah, exactly. So I stopped these trajectories when I was going too far. Okay, so these are all within the regime of validity of the approximation. In particular, you see, this is formally connected to this. You see this one. But I stopped in the middle because you have to go to a region in which the approximation. Yeah.
So the Navy must know all about this because of sonar. Do naval sonars consistently underestimate the depth of submarines?
I don't know. It's a good question. I was talking to some geophysicists, and yeah, I don't know. So they say that in fact they can even, yeah, I don't know. That's a good
Doesn't
question.
sonar just use timing? Doesn't sonar just use timing?
Yeah, but if the pulse, I mean, your
Does
range
change the
finding depends
timing,
on.
But it doesn't, you're establishing the three-dimensional picture.
Yeah.
Maybe it does.
If you
When you say it underestimates,
oh, because the pulse returns high. because it's.
But again, if one knows about refraction, they probably get it right, because
Yeah.
at the level of trajectories, this is a refraction. For sound waves, for rotons, I've never seen this, so I don't know if there is an analogous refraction that one can think of for these crazy particles. These I've never seen. For ordinary waves, refraction is enough to explain the trajectories. Probably.
But if you have a shear, like in the atmosphere, different layers might move at different speeds, and you're an extended object, you can use the shear to accelerate fly. So, but it's called dynamic soaring. That's how big birds fly for days without flapping their wings. So that would be some higher order effect here because it includes the size of the object. But can you use this to write down the next order corrections or something?
No, for sure we can write down this range. I'm not familiar with that case, but yeah, we can think about it. Like, so what is the claim? So if you have some gradient of velocity,
Yeah,
you can
you can extract energy from the gradient, so you can use it to propel yourself.
It would violate your locality assumption, right?
Well, it will be higher orders in the multiple.
Yeah, so there was a multiples, yeah,
Yeah,
exactly.
yeah, you have to start like dipole terms.
Yeah.
Yeah. But do you have to do something because
Actively, not really, no. No, I mean, you have to be in contact, maybe big enough to contact enough of these two layers to use them. The velocity gradient.
The birds do that by changing them.
I don't think they're literally big enough. Well, sailboat doesn't have to do that, so it's possible.
Yeah, but the sail, yeah, that's
It's
true.
true.
That's- I know, it's sailing and sailing.
Right, the sailboat is using the difference in speed between the air and the water.
Yeah, so you can make a
Are
sailboat.
you sure about that, or do we need to test an experiment as a department?
We're pretty sure of that.
Does it work that way in the Mediterranean?
So you have given a first, lowest order description. Do you control the corrections, or it becomes very messy as soon as you start to look at finite size objects, higher order corrections? I mean, do you know the next term in the expansion?
it's a good question. I mean, it should be the same as going from geometric optics in the next correction. I don't know what that is. I've never seen. Here it should be systematic, meaning it's like adding some dipole terms and very quadrupole terms and check how they. But I haven't tried. For instance, even for let's say for a solid object in let's say it's a rigid body, coupled to external fields. Now, if I take into account also the artificial model, can become pretty complicated. Even the spinning top knows kind of a complicated. Maybe it's a fluid match.
Okay, let's think about it.